Hello everyone. So I just wanted to take a few minutes here and go over, as you can see, APC Mechanics 2019, Set 1, Question 1. It's kind of an interesting one where they're dropping this object in a fluid. So that means that it's not obviously free fall. Right? Couple things to pick up in the problem here is that, here's the mass. Note that it's in grams. Nudge, nudge, probably going to have to convert later. Also, that the graph is a speed graph, not a velocity graph. Right? Where that manifests itself is that although the object is falling down, right, the graph is up in the first quadrant, where everything is positive because they're just graphing speed. This is a little bit different of a problem. It's a lab-based problem, but it's a little different in that they give you the original data, and then they draw a curve of best fit through here. Let's keep going. So what this is actually the AP's scoring guidelines. This is their rubric. So it's a 15-point problem, so you can see kind of how they did the points. And I can't really write on it, so I'm just going to talk my way through it. So AI was, does the speed increase, decrease, or remain the same? Well, I hope you look at the graph and say, well, as we go through time, the speeds get larger, so it's increase. Right? That's why it's 1 point. Notice not even a justify. Question 2, in a brief statement, describe the direction of the object's acceleration and how the magnitude of this acceleration changed as the object fell. Well, this is a graph of speed versus time. Acceleration is, of course, the rate of change of velocity, or in this case, the rate of change of speed, which hopefully you know means the slope of the graph. So basically the question is asking you about the slope of the graph. Okay? Now, here's where we need to be a little careful with what I said earlier. I said speed, right? It's a graph of speed, not velocity. So if you look at the slopes of this graph, they are positive slopes. Right? Normally, we would call positive up, but this is not a vector graph. This is a scalar graph of speed. So the object's falling down and speeding up, therefore, its acceleration is downward, as it says down here. Now, I'm not quite sure. One of the things that I like when looking at the rubric is trying to think of, if this is the way they'd actually grade this. It says, describe the direction and how the magnitude of the acceleration changed. Well, to me, if you said the object's acceleration was downward and the acceleration decreased as it fell, notice here because the slope is getting less steep, right, that would be an answer. Right? They also, in their example, give a reason for how you know that. It's moving downwards and speeding up, the acceleration's downwards, the slope of the graph, right, is decreasing, therefore the magnitude of the acceleration must be decreasing. They didn't really ask that in the problem. Right? So I think if you look, though, at their rubric, you can see that what they really wanted was downwards and decreasing acceleration. And remember, a decreasing acceleration doesn't mean that it's slowing down. It means it's speeding up more slowly. I, using the graph, calculate an approximate value for the magnitude of the acceleration of the object at t equals 0.2 seconds. So that's right about here. Again, the slope of the graph is the acceleration. Well, this is a curve. So how do we find the slope of a curve? Well, that's the slope of the tangent line. So they draw in a little tangent line here. I don't know why it doesn't quite touch their little dotted line. It probably should, but oh well. It's an approximation anyway. And then you have to find the slope of that. Okay? As always, you should pick 2 points that are on your, in this case, your tangent line, right, as they do down here. Right? And find rise over run, change in speed over change in time, with, of course, correct units. And you end up with about 2.22 meters per second, or meters per second squared. Little 2-pointer there, right? But notice you have to find the slope of this. Note again how you're using a line of best fit, or in this case a curve of best fit, and you're finding the slope. Nudge, nudge. By the way, you can use a straight edge during the test, right? ruler, in other words. So if you have a straight edge, you can draw this. You don't have to eyeball it and try to draw a straight line, right? Use your ruler and draw a good line and then pick 2 good points on it. And, they're looking for anything that's in that ballpark. Now, here's where the question gets a little more funky. So, the velocity here has a very weird little function. This is a function which is going to come up when we do objects falling with resistive forces that are proportional to their velocity. But you've got this function right here, right? And it models the speed of the object. So this is basically the equation of that curve, right? A curve of best fit. And they give you the coefficients. Here's A and here's B. BI, this is a big one, 3 points. Derive an expression for the magnitude of the vertical displacement, right, of the falling object as a function of time. Now, key here is derive. So it's not just asking you for the expression. If you just give them the right answer, you'll get a point, but you'll lose the other 2 points because you're not deriving it. Deriving in AP lingo means start from basic principles. So if you've got a speed-time relationship, how do you get to the displacement? You take an integral. Right, so you see down here, the displacement is the integral of the velocity with respect to time, and that integral is the integral of this function. Right. Note here, this is how you do an exponential integral. I don't know if you've all gotten to this in your calculus classes or not, but there's the formula, and by the way, it's on the equation sheet. Right, so if you don't know it or you don't remember it, it's on the equation sheet. And basically the integral of e to the ax, where a is a constant with respect to x, is 1 over a e to the ax. Exponentials have weird integrals and derivatives where you get the function back again. Right? So if you follow through the steps here, right, you first have to realize that the integral of a difference is the difference of the integrals. So you take each one at a time. The integral of, and I don't know why they use this dt prime here instead of just dt. I would just use dt, but whatever. Right, so the first one is really just t, because it's the integral of 1 with respect to time. And then the integral of our e to the negative bt is 1 over negative b. Don't lose the negative sign, because these two are going to cancel. Right, e to the negative bt. You have to evaluate it from 0 to t. Right? And those limits of integration here, notice, are part of getting that point. Right? So you do that, and eventually you get down to your answer. And note, they will give you credit if you leave it this way with a and b in, or leave it this way with the numbers. I would always suggest plugging in the numbers since they gave them to you in the setup, but hey, that's how their rubric reads. Kind of the opposite question here. Now they want to know the net force exerted on the object. Well, you can't calculate it directly, but of course we know Newton's second law. And Newton's second law says net force is mass times acceleration. They show that down here. All right, so that means if you know the acceleration and you know the mass, which was given in the problem, I think it was what, 12 grams, then you can find the net force. So the question really is, how do you find the acceleration? Well, of course, the acceleration when you have a velocity time graph, or in this case a speed time graph, is the derivative of the velocity with respect to time. And again, the magic word is derive, so you need to show basic principles, right? Show your steps. The derivative of an exponential function, the derivative of e to the ax with respect to x, is a times e to the ax. If you notice, that's the inverse of what we did before, right? Of what we did with the integral. Again, this is actually on your equation sheet. So if you work everything through, here's the acceleration, plug it into F equals ma, plug all your numbers in, right? And this is what you get for the force as a function of time. Again, you could leave it with a and b and m, or the numbers. Usually, they would want you to plug in the numbers if they gave them to you. All right. So now they are repeating the experiment with a taller glass cylinder. The difference here is that it allows it to go back to, it allows it to keep falling until it reaches what would be known as terminal velocity. Terminal velocity is when a falling object moves at a constant speed. Right? And the important thing to realize is that if it's moving at a constant speed, it's not accelerating. And if it's not accelerating, the net force on it must be, that's right, 0. So that's going to all factor in to the next couple of parts here. So first they wanted you to find the constant speed of the object. Okay, so look at the function for the speed as a function of time. Okay, this is a function of time. So one thing you got to realize here is that this negative bt means that this is really like 1 over e to the positive bt. Right? It's an inverse thing, so it's 1 over that. So when will this speed become a constant? Well, it'll become a constant when this t doesn't really factor in anymore. And when will that occur? Well, since it's 1 over e to the bt, as t gets bigger and bigger, 1 over e to the bt gets smaller and smaller, and therefore less and less important. So if you want to make it 0, you would have to take t all the way out to infinity. Right? So your justification of your answer here is, as it says here in the example, right, it'll reach a terminal constant speed, and that's by setting the time for infinity. So when you set t to infinity, this becomes 0, and the speed is just a times 1, or a. And note, if you didn't write this paragraph here, but you actually just showed plugging in infinity and making it a, they'd give you full credit, of course, because math is a language. Now they want the force exerted, and this is where, as we said before, it's important to realize the terminal velocity means no acceleration, means no net force. So at this point, there's only 2 forces acting, gravity down, and the resistive force of the water acting, of course, up. Right? And so those 2 forces would have to balance. So that means that the resistive force is equal to gravity. Gravity, of course, is mg. Right? So mass times 9.8. This is where you better have your mass in kilograms, because it's 9.8 newtons per kilogram. Right? Or you could just show this. Right? You know, maybe a force diagram, or writing f of r equals f of g equals mg. Plug in the numbers and you get your answer. But one way or the other, there's 2 more points.